Hello everyone and welcome back to another video. Today we're going to start with the AN4 polynomial products outcome. Some of the main ideas in this outcome include understanding what polynomials are, understanding what we can do with them in terms of multiplication, adding, subtracting, and we're going to put a specific emphasis on how we do this pictorially and symbolically. On this page, take a minute or two to see if you can figure out what exactly makes a polynomial. What types of things are allowed versus things that aren't allowed. So what we can do first here is explore some of the things that we notice are the same versus what's different in some of these examples here. So the first thing that we're going to do is we're going to actually highlight some of these negative exponents. Now what makes the negative exponent okay here but not okay, for example, in this particular polynomial or this polynomial? Well, we see here that this -2 is actually attached to the coefficient of 2, whereas these two, the -2's, are attached to the variables themselves. So the first thing that we can say about polynomials is that there are no negative exponents on the variables. Okay, which kind of leads us to some of the other examples that we see here. And we see here that we have x plus y in the denominator, which means that it's on the bottom of the fraction. Same with something like this. We know that back in AN3 we talked about negative exponents. Well, this particular example here is actually the same thing as 2/1 times x plus y to the power of -1. So that's why we aren't allowed to have any variables in the denominator, because really they just represent an expression where there has been a negative exponent applied to a variable. Something else that I want to highlight is also the use of the radical signs here. We notice that the radicals with these two examples are allowed, but something like this and something like this is also not allowed. Now, what's the big difference between them? Well, in these two cases, the radical is actually over the coefficient in each case. So this is the square root of 3, and this is the square root of 4. Whereas in these two examples here, this is 3 times the square root of x. And if we take a look and we go back to AN3, this is really the same thing as 3 times x to the power of 1/2. Whereas this example here is really the same thing as 6x to the power of 1/2. So since we know that these two examples are not polynomials, we can actually go ahead and state that we can only have whole number exponents on the variables. So those are the two big takeaways from what we see here, and we're going to explore it a little bit more formally on the next slide. So let's take a look at a more formal definition of what a polynomial is. Now, a polynomial can have what we call constants. So again, what is a constant here? So a constant is really just a number without a variable attached. So a number without a variable. And we know that a variable is just kind of a substitute for a value that is unknown. And we also know that a polynomial only can have exponents that start from 0. So we have 0, 1, 2, 3, and so on. So to summarize that, we can say that polynomials can only have exponents with whole numbers only, or positive whole numbers rather. So those are some of the restrictions on what polynomials are allowed to be. Now, a key thing to note here is that we can only combine polynomials using addition, subtraction, and multiplication. We cannot combine them using division. And just so you guys know, we're going to add a little caveat to this about combining polynomials with division. We're just going to avoid, more specifically, anything where we have any type of variable in the denominator, as you'll see later on, that we can actually simplify simple polynomials such as monomials divided by monomials using division. So in this example, you'll see that all of the exponents are either 0, 1, or 2. So you have an exponent of 2 here. Anytime where we don't see the exponent, it's implied that it's a 1. We can also, for example, think of this as 3 times x to the power of 0 as well. Of course, we don't see that, so we just consider this as a constant of -3. So we see here that we have 4 terms, 1, 2, 3, 4 terms here, and let's just go ahead and define what a term is. So terms we can define as being numbers, variables, or a combination of the two. That are combined by adding, subtracting, or multiplying. Now that we've got that out of the way, we can think of our 3 main types of polynomials. So we have a monomial. So the prefix mono just means 1. So this is a polynomial with 1 term. Then we can see here that a binomial with the prefix bi means that we have 2 terms. And last but not least, a trinomial means that it's a polynomial with 3 terms. And just as an added side note, any polynomial obviously can be 1, 2, 3, or more terms. So a polynomial we can use to describe anything with 4 or more terms as well. So again, polynomials can include monomials, binomials, trinomials. They are really all just more specific types of polynomials. So to start looking at polynomials pictorially, we were going to use the help of algebra tiles to give us an idea of what exactly we're looking at when we're referring to things such as x squared, x, or 1. So if you guys recall back in junior high, we know that we can use these algebra tiles to kind of help us out. The side length of an x squared tile, we can see here that's x. This is also going to be x because the total area is x squared. Same thing down here for this x tile. We have a side length of 1 here, whereas this bottom portion, the side length is x, so 1 times x gives you x. And obviously with a little cube here, or rather a square, we can see that we have a side length of 1 on each side, giving us a total area of 1. So in this case, we're using green as our positive tiles and a non-shaded set of tiles for our negative tiles. Again, depending on whatever you have on your page, you might end up using shaded for positive or non-shaded for positive. It just really depends on whatever legend you end up using. So taking a quick look at these examples here, we know that this green tile was a positive x squared. Each one of these longer ones is a negative x, negative x, negative x, and then we have a negative 1 here. So adding all 3 of these up, we can see that we have a positive x squared. We are going to subtract 3 of the x tiles, and we're also going to subtract a 1. So we end up with a trinomial of x squared minus 3x minus 1. For the second example, we have 3 of these negative x squareds. We have a positive x, a negative x. We have 2 of the negative ones, and 1 of the positive ones. So adding these all up, we have negative 3x squared. Since we have an x and a negative x, these will actually just cancel each other out. We can say that these 2 will cancel out, so we're left with a negative 1. So our final simplified expression is negative 3x squared minus 1. So let's take a look at a few examples of adding and subtracting polynomials. So in order to add polynomials, we are going to add the coefficients of like terms. So if we think about what a coefficient is, right? If we look at a quick example, let's say we've got 3x squared plus 4x squared as our first example there, our coefficients are just going to be the numbers that are right beside our variable. So it's attached to whatever variable we have here. So we have 3 as a coefficient, and then we also have 4 as a coefficient here. The second part of this is understanding, or remembering rather, what a like term is. So remember, a like term, we have a couple of conditions that the variables and exponents are exactly the same. Okay, so these are terms where the variables and the exponents are exactly the same. We're going to take a look at a couple of examples to kind of clarify that in just a little bit here. So we can see in this example up here that this x squared and x squared are both like terms because we have an x in both, and then the exponent attached to that x is a 2 in both. So we can consider these two terms like terms. So starting off with this first example, we're going to first look at our like terms. So we have an m squared and an m squared. So we're going to add the two coefficients together. We have a 3 plus a positive 4. So 3 plus 4 gives you 7. So you have 7m squared. Next, we're going to take a look at our m's. So we have an 2m plus a positive m. So that gives us plus 3m. And last but not least, we have a positive 7 plus a positive 9. So 7 plus 9 gives us 16, leaving us with 7m squared plus 3m plus 16. In this next example, we're going to see what I meant a little bit earlier by saying that variables and exponents of like terms have to be exactly the same. If we look at this a squared b and the a squared b here, these are like terms again because we have an a squared in both, and then we also have a single b in both. The ab here and the ab here cannot be considered like terms with the a squared b because we are missing the variable there. Okay, we don't have the same, or rather we don't have the same exponent on the a, so those cannot be considered like terms. So we're going to go ahead and add our coefficients. 3 plus a positive 2 gives us 5a squared b. Next, we've got our ab's. So we have ab and ab, which give us our like terms. So here we have a negative 2 plus a positive 4. So negative 2 plus 4 gives us a positive 2ab. Last but not least, we have our b squared and b squared. So we have a 4 or a positive 4 plus a negative 2. So 4 plus a negative 2 is the same thing as 4 minus 2, giving us plus 2b squared, leaving us with a final polynomial expression of 5a squared b plus 2ab plus 2b squared. Now, in order to subtract polynomials, we're going to do pretty much the exact same thing, except we are going to subtract coefficients of your like terms. So we take a look, we have an m squared and an m squared. So 4 minus a positive 2 gives you 2m squared. Here we've got our like terms of m and m. So we have a positive 3 minus a negative 1. So when we subtract a negative 1, we are going to add it. So 3 plus 1 gives us 4. So plus 4m. Last but not least, a positive 2 minus a positive 3. So 2 minus 3 gives you minus 1 or a negative 1. So 2m squared plus 4m minus 1 is our simplified expression. For the second example, again, I'm going to look at my like terms, and we notice that there are a lot of negatives in this expression. So let's just be very careful here. Negative 4 minus a negative 3. So that's the same thing as negative 4 plus 3. So negative 4 plus 3 gives you negative 1. So we have a negative m squared. Typically, we don't put that 1 there because it's just implied that if we have a negative m, it's the same thing as negative 1m. Our next like term will be all of our m's. So we have a negative 5m minus a positive 4m. So negative 5 minus 4, which gives us negative 9m. And then we have a positive 3 minus a negative 8. So since we're subtracting a negative, we are adding it. So 3 plus 8 gives us 11. In our last example here, we notice that we have 3 sets of brackets. That's okay. We can still do exactly the same thing, just making sure we keep track of what's happening with all of our negatives. So here we've got a positive 2 minus 3, that gives me negative 1. Negative 1 minus a negative 6 means that we're adding 6, so negative 1 plus 6 gives you a 5x squared. Next, we've got a negative 3x minus a negative 2x, so that means that we're adding 2, so negative 3 plus 2, and then we're going to subtract 5, so negative 3 plus 2 minus 5. This is the same thing as negative 6x. Finally, we're going to look at the constants here. Well, we just have the one constant. We don't have any other like terms, so we just have a plus 6. In this next section, we're going to take a look at how to multiply and divide monomials, right? So again, this is going to be more of an AN4 review. If you need to go back, check your notes, and look at your exponent laws again, please do so. So in order to multiply monomials, all we're going to do is we're going to multiply our coefficients. So in this case, 3 times 7 give us 21. And then we're going to multiply each of the variables. If you think x times x squared, so using the product law means we're really looking at x to the power of 1. And since we're multiplying powers with the same base, we go 1 plus 2 gives us x cubed. Last but not least, we're going to take a look at the y's. Y times y give us y squared, leaving us with a final expression of 21x cubed y squared. Taking a look at this second example here of 2/3 times 9. Again, a quick review of fractions shows us that this is really the same thing as 2/3 times 9 over 1. So when it comes to multiplying fractions, we go 2 times 9 gives us 18. And then we have 3 times 1 gives us 3. So 18 over 3 gives us 6. So that means that 2/3 times 9 gives us 6. And then we have x times x gives us x squared. So in order to divide monomials, we're going to do more or less the same thing as multiplying, except we are now going to divide the coefficients, and then we're going to divide each variable. So looking at our first example, we have negative 36 divided by 9. That gives you a negative 4. Then m cubed over m squared gives you just m. So again, if you're having troubles understanding why we are left with the result of m, I'd ask you to go back to the AN4 outcome and review your notes from there. Let me know in the comments if you do have any questions. Next, we've got 34 over 17 gives us 2. Then x to the power of 4 divided by x gives us x cubed. Finally, y divided by y, we know that y divided by y is really just 1. So we don't actually put a y here. We could put y to the power of 0, but again, we know that y to the power of 0 is just 1, so we're just going to leave it as 2x cubed. Now the next part of this outcome talks about the distributive property, which is probably the most important part of AN4. Now before we actually give this a formal definition, let's go ahead and take a look at a quick example here. Let's say I have 4 times 5 plus 3 written inside the brackets here. Think about how you would actually solve this problem. Now, according to BEDMAS, we would look at what's inside the brackets first. So we'd have 4 times 5 plus 3, which gives you an 8. And we would just go ahead and say, well, we've got 4 times 8, gives you a 32. Now the question is, well, what if we did this another way? What if we use the distributive property to actually go ahead and multiply the 4 with each of the terms inside the brackets? What that means is I would take the 4 and I would multiply it with the 5. And then I would take the 4 and then multiply it with the 3 and see what the results are. Well, in this case, we know that 4 times 5 gives you 20 and 4 times 3 gives you 12. So 20 plus 12 gives you 32. So we can see that both of these results are exactly the same. Now here's the question for you guys. Why would we do it this second way if we already know that the tried and proven method of using BEDMAS and figuring out the inside of the brackets first would still give you the exact same answer with seemingly a lot less work? Well, here comes the problem. Let's say, for example, we have A and suddenly we have B plus C. how do I actually simplify b plus c if I don't know what b or c are? I can't use this method because I can't simplify what's inside of the brackets, so I actually have to turn to that second way of distributing that 4 inside of the brackets. In this case, I'm going to take the a and I'm going to multiply it with the b. So I've got a times b. And next I'm going to take that same a and now I'm going to multiply it with c. So I've got plus a times c. And when we go ahead and simplify this, well, a times b is just ab, and a times c is just ac. So really what this does is it gives us a way of distributing or multiplying whatever's on the outside of the brackets with everything that's on the inside of the brackets, even if we don't know what each of these variables represents. So when we go back to this page here and we try to define what the distributive property is, it really is just a way of multiplying what is in one set of brackets with the terms in the bracket directly beside it. So we're going to see what I mean by making sure that we only look at the brackets directly beside each other. And we'll see those in a few examples coming up a little bit later on. But looking at some very simple examples with a monomial multiplied by a binomial, all we're going to do is we're going to take that 3x and we're going to multiply it with 2x. So 3x times 2x. And then we're going to take the same 3x and we're going to multiply it with a negative 5. So I'm going to go plus 3x times that negative 5. And then we're going to simplify each one of these separately. So 3x times 2x gives you 6x squared. Then I have 3 times negative 5, it gives me a negative 15. And then I just have the x there at the end. For this second example, I can treat it exactly the same way. I can have 2x times 5x. And then I've got 2x. And then I've got negative 1 times 5x. So minus 1 times 5x. 2x times 5x gives me a 10x squared. And then negative 1 times 5x gives me a negative 5x. One comment that I'd like to add about this question is that we can actually rearrange the order of which we're presenting these terms. So for example, I could have the 5x in the front, followed by the 2x minus 1. This is due to the commutative property of multiplication. So again, this really just means if I take 3 times 5 or 5 times 3, I would end up with the exact same result. So that also applies to when we're multiplying polynomials with each other. For the last question here, same steps apply. We're going to multiply the 8x with the 3 over 2x. So 8x times 3 over 2x. Then we're going to multiply the 8x with the negative 2. So that gives me plus 8x times a negative 2. So when I take 8 times 3 over 2, that gives me 24 over 2, which is just 12. Then x times x gives me x squared. And then 8x times negative 2 just gives me negative 16x. Next, when we divide a polynomial by a monomial, we're going to quickly review how we can work with fractions. Let's say we have, for example, 8 plus 20 all over 2. We have a couple different ways of solving this. Again, if we go 8 plus 20 on top gives me 28 over 2. 28 over 2 gives me 14. I could also actually split this up as 8 over 2 plus 20 over 2. 8 over 2 gives me a 4, and 20 over 2 gives me 10. So again, 4 plus 10 gives me 14. So I could split these up, or I could do these in 2 separate ways that would end up giving us the exact same result. So we're going to go ahead and apply that to our 2 examples here. We see that we've got 20a cubed minus 4a all over 2a. What we're going to do is we're going to split it up first using these two, and then we're going to split it up with those two. So I've got 20a cubed over 2a. I'm just going to put the minus right there in the middle. And then I've got 4a over 2a. So what is this going to look like? 20 over 2 gives me 10. A cubed over a gives me a squared. Then I'm going to subtract whatever the quotient is from here. 4a over 2a gives me just 2. So 10a squared minus 2 is my final result. In this next example, we're going to break it down in a similar fashion, 6x cubed over 2x, and then we're going to subtract 2x over 2x. Taking a look at my coefficients, 6 over 2 gives me 3, then x cubed over x gives me x squared, 2x over 2x just gives me 1, so I'm going to subtract 1. We can use what we've learned so far in some application problems. For example, this first question asks, what's the width of this rectangle? And we're given the area of this rectangle, and we know the length, but we don't know what the width is. So what we're going to do is we're going to use the area formula. Area is equal to length times width. And what we're going to do is we're going to isolate for w. So we're going to divide both sides here by the length. So area divided by the length gives me the width, and that's what we're going to use to help us solve this problem. So since we know that the area is 25x squared over or minus 10x, you've got 25x squared minus 10x. We're going to divide that by the length, and we know that the length is 5x. So we're going to go ahead and split this up just like we did on the previous page. 25x squared over 5x minus 10x over 5x. So what does this look like? 25 over 5 gives me 5x. X squared over x gives me just x. Then we're going to subtract 10x over 5x gives me 2. So your width is equal to 5x minus 2. For the next question, we're being asked about the volume of the tank. Recall that the volume for a rectangular prism is really just length times width times height. If we take this as the length, this is the width, this is the height, all we're going to do is multiply all three sides together. So what I'm actually going to do first is I'm going to rewrite this to look a little bit simpler on my end. So I'm going to take my height, multiply it with my width, and then I'm going to take the length, or put the length in last. What this allows me to do is I can simplify first these two terms. M times 2m gives me 2m squared. And what this does is it allows me to use the distributive property for the rest of this problem. So what that means is I'm going to take the 2m squared, I'm going to multiply it with 4m. So 2m squared times 4m. And then I've got 2m squared times 2. So plus 2m squared times 2. So when I simplify everything, I end up getting 8m cubed plus 4m squared as my volume. So the volume is 8m cubed plus 4m squared. On this page, we have a bunch of practice examples with the answer key down here at the bottom. I would encourage you to work through each of these. Let me know if you have any problems. One thing that I do want to point out is evaluating each expression if you're given the value of a variable. So remember, to evaluate means to find a final numerical answer. So I'm going to work through this one with you guys actually. So if x is equal to 8, that means I'm going to put in an 8 every time I see an x. So instead of having x squared, I've got 8 squared plus 5 times 8 plus 6. So 8 squared gives me 64. 5 times 8 gives me 40 plus 6. So 64 plus 40 plus 6 gives me a grand total of 110. So that's how you would evaluate an expression if you're given the value of a variable. So what we're going to do here on this page is we're going to multiply binomials. So I'm going to put a little star here just to signify how important this part is, because this essentially forms the basis for the rest of AN4, as well as helping you understand what we're doing in AN5 when we actually work backwards and we factor out each polynomial. So when it comes to the algebra tiles method, a couple things that we want to keep in mind is we look at each one of the top and side representations of algebra tiles. We can see here that we've got x plus 3 up on top, and on the side we've got x plus 2. So in order to use algebra tiles, what we're going to try to do is we're going to try to create a rectangular shaped area based off of whatever we have on the top and the side here. And the way that we want to think about this is what's happening when we're multiplying each one of these tiles with another. So if we think x times x, well, that just leaves me with x squared right here. I've got 1 times x gives me a 1, so I'm going to go ahead and put that up here. I'm going to rotate this. And then because I'm going to do that 2 more times, I'm just going to go ahead and paste that 2 more times. I'll do the same thing with the ones here. I've got x times 1 gives me an x. Again, x times 1 gives me another x. And what happens here with each one of these ones, 1 times 1 gives me a 1. So I need 6 of these ones here to complete my rectangle. So what this leaves us with is a polynomial represented by x squared. I've got 1, 2, 3, 4, 5 of the x's. So I've got plus 5x, and I've got 6 of the little ones. So when I multiply x plus 3 times x plus 2, it gives me x squared plus 5x plus 6. Now using the distributive property, what we're going to do is we're going to take whatever we have first in this bracket, we're going to multiply it with that entire second bracket. Then I'm going to take the second term here, the 3, and then multiply with that second bracket. So this gives me x times x plus 2. Since I'm starting off with a positive 3, I'm going to go plus 3. And then times the x plus 2. And then we're going to go ahead and use that distributive property for each section here. So x times x, and then x times 2. So x times x gives me x squared. X times 2 gives me a positive 2x. Here I've got the 3. 3 times x gives me 3x. And 3 times 2 gives me plus 6. We need to remember to simplify by combining our like terms. So our like terms here are 2x plus 3x. So I've got x squared plus 5x plus 6 is my final answer, which matches what we got up here using the algebra tiles. Here on this page, we're going to use a combination of algebra tiles and the distributive property to help us multiply binomials together. Here we see that we're going to end up using our shaded tiles as positive, and let's go with unshaded as negative. So along the top here we have x plus 4 as the binomial we're working with, and then over on the side we've got 2x plus 1. So what we're going to do is we're going to go ahead and fill this in with 2 shaded squares, and then I'm going to do the same with each one of the x tiles that I will need here on the side. Again, since I'm freehanding these, they definitely do not look too pretty. So I've got 8 of these here on the side, and I've got 1 x horizontally along the bottom, and then I have 4 of the ones. I'm going to go ahead and fill these all in as shaded. So we can see here that when we multiply x plus 4 and 2x plus 1 together, we end up getting a result of 2x squared plus 9x plus 4. Let's go ahead and do that using the distributive property. So again, starting off with our 2 polynomials, x plus 4 times 2x plus 1, we're going to go ahead and multiply our first term with our second bracket there. So we're going to take x and multiply it with the 2x plus 1. Then we're going to take the 4 and multiply it with the second bracket. So we go plus 4 times the 2x plus 1. We're going to go ahead and distribute the x. So x times 2x gives me 2x squared. X times 1 gives me plus x. 4 times 2x gives me plus 8x. and then 4 times 1 gives me plus 4. Once I add my like terms together, x plus 8x, we end up with 2x squared plus 9x plus 4, just like we did with the algebra tiles. So with this second example here, we have some negative tiles. So up on top, we've got x minus 3, and then on the side, we have x minus 2. Let's go ahead and figure out exactly what tiles we have here. So here we're going to have a positive x squared. We're going to have 3 of the negative x tiles here. We're going to have 2 more of the negative x tiles on the side. So let's go ahead and fill in what needs to be filled in. So this will be a positive x squared. These 5 x tiles will stay negative because we've got a positive x times a negative 1, positive x times a negative 1, and same thing over here on the side. The only thing that's going to be a little bit different are all of my tiles here on the bottom right. I will have 6 of these positive tiles, or positive ones, because a negative times a negative gives me a positive result. So I have 6 of the positive 1 tiles. So when we take a look and add up all of our terms, we have a positive x squared minus 5x plus 6. Once again, using our distributive property, x minus 3, x minus 2, we're going to go ahead and multiply the first term with that second bracket, so x times the x minus 2. Then we're going to take my second term, negative 3, and we're going to multiply it with that second set of brackets. We'll end up with x squared minus 2x minus 3x, and here we go, the negative 3 times negative 2 gives me plus 6. Once we add up or combine our like terms, we end up with x squared minus 5x plus 6. On this page, we're going to try out a couple more examples of multiplying binomials together. What I'd like to point out about this first problem is that it's actually a lot more difficult than it looks, mainly because of some of the exponent laws that we explored in the previous outcome. When we think of an example such as 4 squared, we know that we can rewrite this as 4 times 4. If we go back to AN4 and we look at an example such as xy, there's a couple different ways we can express this, or xy squared rather. We can express this as x squared, y squared. So what it really looks like is we are imagining that we have x to the power of 1, y to the power of 1, and all we're simply doing is we are multiplying the 1 by 2 to give us this 2, and the 1 times 2 to give us this 2. What's really happening with xy squared? This is really the same thing as xy times xy. And we can rearrange what we have here to give us x times y, which eventually leads us to x squared y squared. Now the problem with this is that it gives you a false idea of what this simplifies to be. Most students are simply going to say, well, I can just do the same thing. This is x to the power of 1, 4 to the power of 1, and we're just going to simply write x squared plus 4 squared, which is actually very incorrect. Instead, we're going to look back at this initial example where we had xy all to the power of 2. We took what was inside of the brackets here and we multiplied it by itself twice. So we take what's inside the brackets and we go xy times xy. That logic is still the same here. We're going to take whatever is inside the brackets and we're going to multiply it by itself twice. So x plus 4 squared is really the same thing as x plus 4 times x plus 4. If there's one big takeaway from this outcome, this would be it. So please remember that if we have something squared, we're going to simply expand it by multiplying it by itself twice. From here, we can just use the distributive property. We're going to take this first term, multiply it by that second bracket, take the second term, and multiply it with the second bracket. And we'll end up with x squared plus 4x plus 4x plus 16, which eventually simplifies to x squared plus 8x plus 16. In the second example, we're going to look at two binomials with two variables. So we have a 3s minus 5t times 2s minus t. The rules don't change at all. We're just going to take this first term and we're going to multiply it with the second bracket. We're going to take the second term, so minus 5t, and multiply it with the second bracket. We have 3s times 2s gives me 6s squared. We have 3s times negative t. We just simply have minus 3st. Negative 5t times 2s gives me negative 10st. And then we have a negative 5t times negative t gives me positive 5t squared. After simplifying and combining our two like terms here, we get 6s squared minus 13st plus 5t squared. Something that I like to point out is even if we have something such as 13st and 2ts, we can still combine these as 15st or 15ts. Again, the order doesn't really matter in which we present our variables, right? Because of the commutative property, we can switch up the order that we multiply them. They would still give us 15st. Again, for this last example, because of the square here, we're going to expand this first, like so, 4m minus 6n times 4m minus 6n. We're going to take our first term and multiply it with the second set of brackets. Take the second term, multiply it with that second set of brackets, and then we're going to simplify. So 4m times 4m gives me 16m squared. 4m times negative 6n gives me negative 24mn. We have negative 6n times 4m gives me negative 24mn, and then negative 6n times negative 6n gives me positive 36n squared. Simplifying our polynomial here, we have 16m squared minus 48mn plus 36n squared. In this next section, we're going to go ahead and multiply binomials and trinomials together. What we're going to keep in mind is we're still using that distributive property to allow us to do so. In this example here, I'm going to take that first term, the 5x, and I'm going to multiply it with everything inside that second set of brackets. So that gives me 5x times x squared plus 2x plus 1. And then I'll do the exact same thing with that positive 2. So I'll go plus 2, and I'm going to multiply it with everything inside of the brackets again. So I've got the x squared plus 2x plus 1. From here, I can go ahead and use the distributive property to multiply that 5x into everything inside the bracket right beside it. I don't do the same thing to the green, right? If we think about it like this, if we have 4 times 3 times 2, I would take these two first, I would multiply 12, and then I'd have times 2 gives you 24. I would not do this. I wouldn't go 4 times 3, which gives you 12, and then I wouldn't go 4 times 2 to give you 8. I would not do that, right? That would be very, very incorrect. So please make sure you don't do the same thing with polynomials. So once we've gone ahead and multiplied these out, 5x times x squared will give me a 5x cubed. 5x times 2x gives me a 10x squared. And 5x times 1 gives me positive 5x. I'm going to do the same thing here with this positive 2. I'm going to distribute it by multiplying it into this bracket here with each term. So 2 times x squared gives me a positive 2x squared. 2 times 2x gives me a positive 4x. And 2 times 1 gives me a positive 2. From here, I'm going to look for my like terms. This is the only x cubed here, so that's 5x cubed. I have a 10x squared and a 2x squared gives me 12x squared. 5x plus 4x gives me 9x. And then I have the 2 by itself. So this would be my final simplified form. I don't have any like terms that I can combine together. So this will be my final simplified expression. I encourage you to try out these 3 problems on your own by pausing the video and then unpausing once you're ready to check your work. Once again, I encourage you to pause here and try out the next 3 questions on your own. Once you've completed the work, go ahead and unpause and check all of your solutions. Let's take a look at the first of our 2 application problems. We're going to let x represent the width of the picture frame, which means that this portion right here, so this entire red line, is going to represent x. The first question asks, what expressions would represent the length and width of the picture within the frame? So now we're going to look at this portion right here, and we need to be able to figure out how long that portion is. So what we're going to notice here is we're really looking for the width right here, and we can see that since this portion and this portion are 3 centimeters each, we're actually going to subtract a total of 6 centimeters off of our x. So that would mean for us the width of our picture frame, or rather our picture, can be represented by x minus 6. If we look at our length, which is going to be this green line right here, we can notice that since we're looking at a square picture frame here, this entire thing, or this entire side length, is actually x. Because we're only looking for this green line, we can subtract the 2 centimeters found here and the 2 centimeters found there, leaving us with a length of x minus 4. Since we are taking off 2 centimeters from the top, 2 centimeters on the bottom, so you got x minus 4. For the next problem, we're being asked what expression would represent the area of the picture within the frame. We're going to go back to an area of a square or a rectangle, whichever way you'd like. We have area is equal to length times width. Since we're going to be multiplying those two measurements together, we get area is equal to x minus 6 times x minus 4. We can go ahead and use the distributive property to help us figure out what the area of the picture is. So we're going to take that x, multiply it with x minus 4, take this negative 6, and multiply that with the x minus 4. Let's go ahead and simplify. X times x gives me x squared. X times negative 4 gives me negative 4x. Negative 6 times x gives me negative 6x. And negative 6 times negative 4 gives me a positive 24. Simplifying my two like terms, the negative 4x and the negative 6x gives me minus 10x. And then we have the plus 24. So the area of the picture is x squared minus 10x plus 24. Next, if we're looking for the area of the entire frame and the picture, well, again, we're just looking for length times width. Now just recall, since we know that the entire bottom length is x and the entire side length here is also x, our area really is just x times x, which is x squared. So that would be the entire frame and picture combined. Now, if we're looking for the frame only, we're essentially just looking for this portion on the outside. So this would be this purple portion right here. So what I'm going to do first is create a formula. So the area of the frame, so AF, area of the frame, is equal to the area total, or the total area, minus the area of the picture. So the area of the frame is equal to our total area, which was the x squared. And then we're going to subtract the area of our picture. So if you guys recall, we have x squared minus 10x plus 24. Now what's really important to note is we're going to subtract this entire thing inside of the brackets here. And then we're going to go ahead and simplify. So the area of the frame is equal to x squared minus x squared, so that would actually leave us with 0. We're going to subtract a negative 10x, which leaves us with a positive 10x, and then we subtract a negative, or rather we subtract a positive 24, so 10x minus 24 is the area of the frame only. For our second application problem, we're looking to find the shaded area only. Now what we're going to do is we're going to come up with a strategy to help us figure out how do we only isolate this shaded portion and not include this unshaded portion. What I'm going to do first is I'm going to draw another rectangle here, and I'm going to simplify our dimensions. We're going to take the dimensions that we have here, or the measurements that we have, and we're going to combine them. So we have 6x plus 8. And we're going to add the x plus 2. So that means that the total length up top here is actually 7x plus 10. Here on the side, we're going to add this side length of 3x plus 1, and we're going to add it to the 3x squared plus 5x plus 3. So that leaves us with 3x squared plus 8x plus 4. If we were to look for this entire rectangle here, we can call this the total area. What we're going to do next is we're going to look for this unshaded portion. So let's call this the unshaded portion. So AU, which will be this little box right here. So what we're going to do is we're going to multiply the two side lengths. We have 3x plus 1 times the x plus 2. We multiply these using the distributive property. We end up with this, the 3x times x plus 2, plus the 1 times x plus 2. So the unshaded area, we get 3x squared plus 6x plus x plus 2. So the unshaded area is just 3x squared plus 7x plus 2. We're going to put that aside for now. And we're going to go back to our total area. And we're going to multiply these two out. So the total area will look something like this. We have the total area being the 7x plus 10. And we're going to multiply it with the 3x squared plus 8x plus 4. Once again, I'm going to take the 7x, the first term, and I'm going to multiply with everything inside of here. So the total area is 7x times the 3x squared plus 8x plus 4. And then we're going to take the 10 and multiply with everything inside of the brackets there. Let me move this to the side, give myself a bit more room. So we have plus 10 times the 3x squared plus 8x plus 4. So I can go ahead and simplify this expression using the distributive property. I'm going to take the 7x times 3x squared gives me 21x cubed. 7x times 8x gives me 56x squared. And 7x times 4 gives me plus 28x. For the red portion, I've got 10 times 3x squared gives me 30x squared. 10 times 8x gives me plus 80x. And 10 times 4 gives me plus 40. I will go ahead and simplify all of my, or combine all of my like terms. The 21x cubed is by itself. Then I've got the x squared, the 56x squared, and the 30x squared gives me plus 86x squared. The 28x plus 80x gives me plus 108x. And then I just add the plus 40. So my total area is 21x cubed plus 86x squared plus 108x plus 40. So let's come up with an equation to help us figure out what that shaded area will be. So the shaded area will be equal to the total area minus the unshaded area. Let's go ahead and plug in each of those values. So the shaded area is equal to the total area. As we go back up here, we know the total area was 21x cubed plus 86x squared plus 108x plus 40. And we're going to subtract everything here in brackets. So we're going to subtract whatever the unshaded area was, which was 3x squared plus 7x plus 2. So let's go ahead and combine our like terms. The 21x cubed is by itself. 86x squared minus 3x squared gives me plus 83x squared. 108x minus 7x gives me plus 101x. And then 40 minus 2 gives me plus 38. So our final shaded area will be 21x cubed plus 83x squared plus 101x plus 38. If you guys have any questions or comments, please leave them down below. Thank you so much for watching, and I'll catch you guys in the next video.